CAN bus, Controller Area Network, is a robust communication protocol originally developed by the Robert Bosch GmbH company in 1986 to be used as a vehicle localized network, allowing all electronic control units, ECUs, to communicate with each other using a single data bus, thus drastically reducing the amount of wiring. Thanks to its incredible fault tolerance, the standard has been recently adopted by 3D printing community and is currently supported by many devices and accessories used in modern 3D printers. This particular CAN to SPI module, based on Microchip's MCP2515 IC, is a very popular device that allows to add CAN connectivity function to your system. I purchased it because I was modding my 3D printer to operate the toolhead via CAN, which, I should say, is totally worth it. The 2515 CAN board itself is dirt cheap and available on many online marketplaces, including Amazon and AliExpress. It basically consists of the MCP2515 CAN controller chip and the TJA1050 CAN transceiver, which talk to each other. Then, the TJA1050 hooks up to your CAN network, and the MCP2515 is connected to the uplink, your host computer board, via the SPI 3-wire interface. This module was initially designed to be used with Arduino, which means it's using 5-volt TTL levels for the uplink connection. However, if you plan to use it with an SBC, like Raspberry Pi or Orange Pi, you're gonna need 3.3-volt levels. Does voltage matter here? Well, yes it does. And it boils down to this. If you power the CAN module off a 5-volt source, the link might work. But the Pi will not be happy because you'll be pulling its inputs above its supply voltage, which is something you shouldn't do in electronics engineering. On the other hand, if you use 3.3 volts to power the CAN module, the MCP2515 to Pi link will be fine, but the TJA1050 CAN transceiver will be underpowered, which may result in data loss and corruption over your CAN connection. So, how do we solve this? All we have to do is provide separate power for the TJA1050 chip. By good luck, the PCB is not at all complicated. Let's see. The power from the VCC pin is fed to pin 18 of the 2515. It also arrives to pin 3 of the 1050. Note that the two ICs on this board are oriented with their pin 1 indicators facing each other, which is sort of not typical. Anyway, pin 3 of the TJA1050 is connected to the C5 capacitor and then to this via, which goes to the only trace found on the bottom side of the PCB. And it arrives right here, to pin 18 of the MCP2515. So, all we have to do is cut this trace. Then the VCC pin becomes 3.3 volt power for the CAN controller, and here we're gonna have to attach a jump wire through which 5 volts will be fed to the TJA1050 IC. You don't really have to be too careful when cutting the trace. It's okay if you cut the area around it. It's connected to the ground rail basically. What you do have to look out for is that the edges of the cut trace do not touch the ground area surrounding it, because this will result in a short circuit. Also, do make sure you cut the trace properly. As you do it, wash with alcohol for better visibility. And, as usual, in electronics, we don't trust what we see. We always check with a multimeter. Good. Now pin 18 of the 2515 is connected to the VCC pin of the interface connector, and this becomes our 3.3 volt power. To supply power to the TJA IC, I'm gonna solder a pin from a standard DuPont connector. As we can see, there is a capacitor between pins 2 and 3 of the chip, but we're still gonna solder to the IC directly, because its pads are a tad bigger. Now, the board may be subject to vibration, so I'm going to use some glue here and also a small DuPont plastic pad. And glue again. Let it dry before you proceed. Good. One more thing. I would like to run my CAN bus at 1 megabit per second, because that's the default bitrate in Klipper and most CAN devices used in 3D printers. However, the 8 MHz crystal installed here will allow us to operate at 512K max, per the IC specs. So I'm going to replace the crystal with a 16 MHz one. It might be a bit challenging to remove factory soldered parts, but I will share with you a couple of simple tricks. First, apply some liquid rosin. This will improve thermal contact with the pads. Then set your iron to about 400 centigrade. Factory boards come soldered at higher temperatures. And here's the most useful one. Apply some of your regular solder to thin out the factory solder. Rock from side to side very gently, and there you go. I'll borrow the 16 MHz crystal from an Arduino Mega board here. I got a whole stack of them in my drawer. Now, while working on the crystal, do make sure you're not squeezing it too hard or pulling too hard. It's a sensitive device and you don't want to ruin it by being too harsh on it. If it's not coming out, do not apply force. Just take your time. We are ready to install the new crystal now. Remember to set the iron back to normal temperature. I use 330 degrees Celsius. Good. To connect the board to the Pi, we can use this diagram. As you can see, a total of 5 signal wires will be used. And also ground, 3.3 volt rail and 5 volt rail. The SPI bus on the Pi board is hardwired. It uses GPIO pin 11 for clock, pin 9 for SO output, and pin 10 for SI input. We'll also be using the CS chip select attached to pin 8 and the interrupt signal wired to pin 25. The interrupt pin is needed to inform the host that the CAN module has some data in its buffer and it wants it to read it. We're all set with the hardware now. Time to modify the OS settings. The SPI bus is not plug-and-play type. It's merely a digital TTL level interface. So, to make it work, we must tell the system which pin the INT line is connected to, and also, that's very important, at which frequency the crystal on the CAN module is running. These are the exact edits you have to make. The SPI max frequency tells the OS how fast the SPI interface can run. Note that we set it to 5 million instead of 500,000 it's set to by default. You can raise this number to 8 million if you got errors on your CAN bus. After reboot, the OS should be able to detect the CAN board. If it doesn't, please recheck your wiring. Another thing we modify is the QLEN setting. That affects data transmission from the host to CAN devices. The Klipper recommended value is 1024. At this point, you have to set up Klipper according to the manual that came with your CAN gear. In my case, both the Toolhead MCU and the Cartographer 3D sensor, which also runs via CAN, are detected properly. Note that the machine runs on the Raspberry Pi 3B board, which is actually more than sufficient for Klipper, on condition that you don't use its USB interface to talk to your MCU boards. Apparently, there's an issue with USB bus on Model 3 that causes disconnects, data errors, and failed prints with USB CAN modules. But I'm using CAN via SPI now, and it's good. And last but not least, you can actually avoid the voltage mod we did today if you replace the CAN transceiver IC with a newer one. The SN65HVD230 is basically pin compatible with the TJA1050, but runs solely off 3.3 volt power, So, if you have one of those, you can use it as a drop-in replacement and just power the entire CAN module using Pi's 3.3 volts rail. Please let me know in the comments what you think. And also, don't forget to like and subscribe. Then, if you found this video useful, please consider supporting the channel by donating any amount of Bitcoin or Ethereum that you believe would be reasonable. The wallet info is pinned in the description.
This was Ron Martino.
Be good.